Okay, so we're going to talk a little bit about the logistics. The screens are on. So we haven't posted the assignment yet. We will do that before the next lecture. We have discussed with Christopher that we need a little bit more time to make it so that we don't change it much. Last year we've posted the assignments, but we have to adjust them because we were trying them out after posting them. So this time we will try them out before, so then they will be more stable. That was the idea. And also Bjorn can try it out and so on. So that's one thing. The first assignment is relatively straightforward, so shouldn't be a big problem. So I will post it on the GitLab website. The second thing is that we will have some activities, and we already have some activities in the class. So one of them is putting questions and issues here. And we still have 0, so like it seems like nobody has any issues with anything, which is not true. The other thing is that we will use peer review for evaluation of some of the assignments, or maybe even all of the assignments. We have tried it last year with the mobile course, and it worked quite well. It works like this, that you have to check somebody else's assignment and say, oh yeah, they've done it all correctly, or you say, no, they haven't done it all correctly. So you kind of mark them. And then if they are marked, then you put your entry into kind of a big spreadsheet, and we've used 3, right? 3 or 2?
Two PP.
Yeah, two peers. So each person was evaluated by 2 peers. So for each assignment, you will do 2 checkings. And the idea is that you kind of contribute to the social aspects of the course. So we have multiple aspects, like, participation in the class, you asking questions, you discussing. We kind of don't keep track of that. We have the issue tracker and answers and questions on the GitLab, which we do track who is contributing what, and we will have the peer review, how many additional tasks you've done for the assignments, and we track those things. And then at the end of the semester, you get a grade for the internal portfolio, and the internal portfolio consists of the assignments that you've done and the contribution, the social contribution that you've done to the course. And the model that we've used last year is that we've calculated the average of the social contributions, and then people who contributed more, they got extra bonus points for the internal portfolio. And people who contributed less than average, they are called free riders because they do less than they should. They were getting some negative points for contributing to the class. Last year, it was a little bit controversial. So I'm open for suggestions of how to do that, and whether you like the model or whether you would like suggest something different. Okay? So what do you think? Is it fair to have something like this, or do you like something different? The idea is that, if everybody contributes around the same, around the average, then that doesn't change anything. But if somebody is not really contributing or free riding, then they get a little bit of punishment. And then if somebody is doing a lot of work and contributing a lot to the class, gets kind of a reward. So, yeah?
What's your contribution? Is it just how many messages someone posts?
No, it needs to be qualitative.
Yeah.
So for example, last year we had some kind of really proactive activities. For example, you guys are right now, or some of you are struggling with the Linux setup and so on, right? So we had one student who was in a different course though, that posted pretty much a tutorial on how to do it properly, and that pretty much helped eradicate all the other problems. So that was really a qualitative contribution to the class that was measurable and meaningful. Just opening as many issues as possible probably doesn't help you. But if you ask good questions, however, that no one else asked, right? So and we kind of earmark this and can address it in class. That's a qualitatively valuable contribution, even though you're not answering anything, but actually asking a question, right? So it's about this. If you ask, oh, my sudo is not working, what should I do? Then, yeah, that's more like you get support, which is good, but it's of course some sort of, the contribution may arise if there's a discussion following on, but in itself it's probably not that valuable of a issue. So that's the intuition.
So yeah, so quality and quantity. So quantity alone is not, you know, sufficient. You can write a really good sort of a tutorial, and then that's just one, but it's kind of good quality, right? The other thing is that those extra kind of bonus marks, they don't really change your grade, right? So if your portfolio is like C, you're gonna get C no matter what. But if your portfolio is kind of on the boundary, those extra grades will push you over, right? So if you're kind of between A and B and you've contributed, then it will push you over to A. But if you B, like in the middle of B, and you've contributed a lot, it's very unlikely that it will push you to A. It's sort of just for those border cases. So it's kind of additional thing. So it's not like really big deal, but well, it kind of turned out it was big deal last year for like 3 students who were on the boundary and they didn't go bumped up, right? Because they were kind of free riding. So they had colleagues who did exactly the same, and the colleagues were bumped up, and those 3 people were not. So they came and asked, well, why we were not bumped up? And we said, well, because you were kind of not contributing, right? So that's how it works. So if you think it's okay, we will use it. I mean, it doesn't matter yet. It just matters at the end of the course. But bear it in mind that if there are you have some idea to explain something, or if you have problems with something and you found a solution, just post it, and that helps the rest of the class, and it kind of helps you as well. That's the basic idea. Any questions or comments about this? All right. Yeah, for the peer review, we will tell you on Tuesday how it's gonna work, and we will tell you what the assignment 1 and 2 probably are. Right. Any organizational comments or questions? So who has already finished the Linux setup and are comfortable with the command line and with the Linux? Okay, so most. Who has done the programming tasks? How far you got with the programming tasks? So who is up to, yeah, we did 4 in the class. Yeah, we kind of did that. So who did everything? Okay. Who did the tutorial from the Golang? Yeah. Any questions? Like, did you have any problematic topics that you want to have some time me talking about? Yeah. All right. So the rest, why didn't you do the tutorial? What's the reason of not doing the tutorial? It takes too long, or what? Are you too lazy? What's the reason? Say it again?
I've done the tutorial to the degree that I can, but
okay. So most of the things you can do in a browser.
Yeah, I did do the browser.
Yeah.
I just prioritized the other classes.
Okay. Yeah, it's a good start. Like, it will help you later. Programming is something that you cannot speed up. So certain concepts and certain things you have to they have to settle. So it's kind of like learning a foreign language. If you have to spend 3 hours and you spend it in 1 day, it's less effective than if you spend 15 minutes over a period of 2 weeks, right? Every now and then. So it's better to come back to it for 15 minutes and do a little bit, and then let it settle, than to cram it into like a 2-hour session. You will learn less. For programming tasks, for like coding, it's better to cram it, to dedicate like a very long block of time where you kind of sit and dedicate it for solving tasks. But for learning, it's not. For learning, it's the opposite. It's better to spend short amount of time on a regular basis. All right, so what we will talk today is we will continue with the lecture for the third time. We've been a little bit slow in getting it sort of completed. So last time we got to passing by value, passing by reference. We explained how that works, where we use what, and we showed different ways of building methods. So we talked about structs, and we talked about functions which take a struct as a parameter, or functions which are called on behalf of a particular struct, which we called methods, right? So the functions which are just called with a name, we refer to them as functions, and then they can take a struct as a parameter, and functions which are called with this dot notation, like in C++ or Java, we call them methods. So those are functions with a struct receiver. We haven't done the interfaces yet. So what is an interface? Do you know the concept of interface from other programming languages? Yeah?
It's kind of like a class, maybe?
Yeah.
You can add functions to our structs.
So what the interface doesn't have?
Implementation.
Yeah. So the interface doesn't have the actual implementation or any state. It's like a declaration of access to a particular class or object. So it's a list of signatures of methods which can be done, but it doesn't have any behavior associated with it yet, because this interface can be associated to different types, to different structs or different classes, right? So here we have an example. We have, so to declare an interface, you say type, your name of the new interface, and then instead of struct, you say interface, sorry. And we have a simple interface, which is just one method. That method is called area, and it returns a floating point number, right? So it's sort of, the interface is called geometry. It returns a float when the method area is called. And then we have a struct, one which is a rectangle and one which is a circle. And, clicking. And the rectangle has two properties, width and height, and the circle has one, just radius. And they both implement that interface. Those of you who know Java, when you're creating a class that implements particular interface, you have to say, class, my class implements interface, right? In Go, that is inferred. You don't have to say that. Any struct which has the method area on it will become part of that interface, yeah?
How do you infer which interface to implement if there are multiple interfaces with the same
method?
methods?
How
do you distinguish between which interface if the context, if there is different contexts for it?
So I think I'm not sure, I haven't tried that, but I think it will use all. So if I have multiple interfaces that have this signature, and my struct implements that method, it will belong to all of those interfaces. So it will have like a multiple types that it can pretend to be, right? So it infers all of them, and then your struct can become anything that has this method, right? So if I have another interface which has a method area, and my rectangle has the method area, then it can pretend to be geometry, or it can pretend to be this other interface as well. It just works. So, so here I have two structs, and both of those structs implement the method area, right? So rectangle has the method, and it just calculates the area of the rectangle, and then the circle has the area, which calculates the area of the circle. And then I have a method which accepts geometry, right? So the method doesn't accept any struct. The method accepts the interface. And then my structs, R and C, can be passed to this method. So I have polymorphic behavior because I have a method, or actually I have a function, which accepts multiple types, and it can accept both rectangle or a circle as an argument because they both implement this interface, right? And as I said, this is done kind of automatically. It's inferred from the declarations of your methods on the types that you have. So this is very similar to Java or to other languages in which you have polymorphic behavior, in which case you don't need to know what type will be passed here at runtime. It just has to conform to this, it needs to have this method that the interface has. And interfaces are quite heavily used in Go. They usually are very simple, 1 or 2 methods, and they are usually named with ER at the end. So there is an interface which has a method string, and it returns a string, right? And this interface is called stringer. And most types and most structs that predefined types have that interface, and it allows you to print some information about the type. So if I have a student, it's good to make it part of the stringer interface, because then you will have a method string which will print what it is. In this case, I didn't name geometry with ER at the end. You could call it area or something, but it's a little bit weird. So if the default naming convention doesn't fit, then you use your own. But if you can make it into ER based on the signature of the method, then it's sort of the typical way of doing that. So this is kind of so this mechanism, together with mechanism of methods on top of the structs that you have, provides you all the facility of object-oriented paradigm. You can model your domain using structs, using objects, and then you can have behavior attached to those structs, and you can have polymorphic behavior based on the notion of interfaces. What do you don't have? We discussed that in the first class. So compared to Java, for example, with those mechanisms, you can almost do everything, but you still don't have one thing. And in C++, you can also do that, but here you cannot. What you don't have? What's one of the typical things you do in object-oriented programming? Yeah? Say it again? Yeah, I mean, the class here is kind of like the struct with the behaviors, right?
Well, in normal object-oriented, you have inheritance.
Exactly. There is no inheritance here, right? So, because there is no inheritance, how you deal with that? So what if I had okay, so for example, between the rect and the circle, we can see that the circle is kind of a simpler form of a rectangle. You could kind of push the definitions like that and say, for circle I only need one field which contains a float. For struct I need 2 fields, right? So I could have that the rectangle is kind of an extension of a circle because it adds this extra field, right? I mean, here it doesn't make that much sense because actually circle is, conceptually something different. But, we could do that in C++. We could declare a base type, which would just have one field, one attribute, and then this one would extend it with 2 attributes, right? Here we cannot do that. So, what do you wanted to ask?
What I would suggest is to take the circle to 3 dimensions.
Yeah.
You have a sphere and you have a tube.
Very good. So that would make sense, right? So if I have a circle and I have one, yeah, but the sphere also has just radius.
This has the exact same interface while the tube has a length as well.
That's true. Yeah, but again, it is kind of
You have the same interface for the radius.
yeah.
That's my point.
Yeah. So imagine that you have a sphere and you have a tube which is made by the sphere being kind of moved, so it has kind of a round on both ends. Then it kind of makes sense. So you have a sphere which has a length 0, which is just a sphere, which would be called a sphere, and you have this this rod, which is kind of an extended sphere. Yeah. So how would you do that? How would you do that in C++ or Java? You would have a data type which says extends sphere, and then adds this extra thing and has some other properties, right? Like rotation and things like this. How would you do that in Go? Right, so let's have a look. I will go to my Go. I have so I have some problems. I will ignore it for now. So we have a sphere. So let's say I have a sphere which has radius, which is a float. And now I can do some things with the sphere, and I need another type which extends the sphere, right? So I need this kind of a rod type, which normally I would say when would I have inheritance, I would say, yeah, rod extends sphere and adds extra field. And this extra field is, let's say, length, which is a float as well. So because I don't have inheritance, what I do here is I would say, actually, rod extends sphere by having a sphere field inside the rod, right? And then I can reuse everything sphere has inside the rod. And I don't even need to give it a name, I just put a type. I can give it a name as well, I can put S. But if I don't, then what will happen is I will have a rod now. So if I say I have R, which is a rod, and I will have a field which is sphere, and I can access my radius of the sphere like this, right? And then I can access the length like this. So even though I don't have inheritance, I can reuse my data structures that I created by delegation, right? So that's how Go solves the problem of lack of inheritance. It basically substitutes inheritance with delegation and kind of a composition, right? Is it simpler? Yeah, I don't know. We were discussing it that, you know, inheritance has some advantages for some well-defined hierarchies of types, but for the maintenance of the code and when you're changing requirements and so on, the inheritance is a bit cumbersome and it often leads to problems. This is simpler. It's a simpler model and it's easier to maintain, it's easier to adapt and easier to change. So yeah, the decision when they were designing the language was to use this. Okay, any questions about interfaces and composition? Great, so we will move on. concurrency. All right, so this is an interesting topic. We will only talk about fundamentals. We could spend an entire course on how to arrange and organize and architect concurrent programs. We will just talk about basics. So there's a good introduction to channels and to concurrent programming. What's interesting is that the concurrency is built into the language. So in most languages you have to have a library or you have to have additional support. But in Go it's part of the standard libraries. And it's actually part of the syntax of the language. So if we try to do some simple things concurrently here. So let's say I have, yes, I will delete that, delete our roads. I will say we are done quitting. So we will print something at the end. And now let's say I have a function that prints numbers up to max. So I will say for x equals, yeah, so I can do this from 0 to x less than max, x plus plus, format print line x. So if I say print numbers, well, 10, print numbers 10. What's gonna happen? What I will see when I run this program? Prints, good, so I will see the compiler doesn't compile. Prints numbers, prints, yep, okay, better. What will I see now? Good. From 0, yeah. So I see from 0 to 9 and from 0 to 9, okay? So I have a sequential program which executes this function and then executes this function and then prints that and quits, goes here. So to make those two functions run concurrently, I can just say I want them, I want them to run in a separate threads, and I will prefix it with Go. And that means they will now run independently of the main thread, right? So what will I see now? Yeah?
It depends on the schedule in which process gets laid out within the CPU.
Yeah. Good. So let me do one more thing. So I will save. Okay. All right. So let's run it and see what happens. So it says 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 5, 6. Yeah, they shuffled, right? So one of the threads got up to 4, the time slice, and then the scheduler said, oh, wait a minute, you're taking too long, now let's run the second one. The second one started, and we don't know, you know, is this 5 from the first one or from the second one, because we don't know. So we could, yeah, that's right. We can add additional printout to see which one is which. So let's do that to be sure. So let's take like a tag. Come on. So let's take a tag which is a string, and we will print. We'll print tag with X, and then we say we have A thread and B thread. So now we will see how they go. So yeah, the numbers are so small that B got first all the way, and then A got again. Let's run it again. Yeah, same story. Same story with the 9 missing. So B got to 8 and then got put into background, and A got executed all the way to 9, and then B got again. So it's shuffled somewhat. The numbers are so small that the loop is very fast. So that's why, you know, doing the initial bum is kind of the slice that the operating system allocates. Okay, I added an extra thing here which waits for me to press enter before the program quits, right? So if I execute it again, notice that the program prints, waits for me to press enter, and then prints we are done, okay? What will happen when I don't have it? So what will happen if I, if I comment that out and run now? Yeah?
I'm not completely sure, but I think the main thread system will continue execution, and then we are done.
Yeah.
And then both of them, we grab 2 threads, that thread keeps running, and then we're going to print the numbers.
Yeah, very good. Any other ideas?
It might depend, but since the main loop then exits, it might actually terminate all threads as well.
Exactly. So we have 2 options, right? We have one option which says the code gonna execute this, start preparing a new thread for this routine. It goes here, it starts preparing a new thread for this routine. That takes time, right? While this is taking time, the main thread continues, prints this, goes in here, and then we have 2 options. One option is that then it waits for those 2 threads to finish, and then they will print whatever they need to print, and then the program will quit, or that it kills them and quits immediately, right? So let's run it. So let's run the program. And what happened?
Last option.
It's the last option, right? So what happened is we started scheduling thread A. We went to printing, actually we started scheduling thread A and scheduling thread B. While the runtime was trying to create a new thread, we have printed the we are quitting method. So the last line got executed, right? Then before the last line was executed and we got to the closing bracket, the first thread started executing its function. The B thread hasn't started yet, but A started. And A managed to do 4 prints before everything was killed and the program quit, right? So this situation actually is a bug. It's considered a bug. If you have running threads while you're hitting the closing bracket of your main loop, yeah? Yeah. Yes?
Can you store the reference to the thread and wait for it to complete before you, so you don't have to damage it using sequence?
In some way, yes. Right? So we will do that. So this situation where you have some running threads while you're closing the main thread is considered a kind of a bad programming practice. when you're closing the main thread, you should tidy up. You should make sure that nothing else is running. And then if you run some of the tools, they will tell you that your program has still running threads while the main loop is finishing, therefore you have to fix it. So we need to somehow tell the main thread that we are done with the printing, right? So how can we do that? There are multiple ways of achieving that. One was that I basically stopped here, right? But that's not a very robust solution. It actually doesn't know if the printing has happened. It will just, like if I press enter too quickly, I will have the same problem because I don't know if those two loops finished or not. If I make a very large number here or if I loop infinitely, then it will still be killed because reaching this line, right? So one way of solving this is to use channels. And a channel is kind of a very simple concept. It's sort of like a pipe into which you put values in one end and take them, read them from the other. So it's sort of like a queue. The default pipes don't have any buffer, so they kind of very flat. So they can only put stuff in if someone can read it out. If no other threads are reading stuff out, the thing which goes through the pipe cannot go through. So you can imagine that it's sort of like a pipe of 0 length, right? You can only put stuff into it if someone else will kind of read from it. Otherwise, this will block until someone wants it, right? I can make the pipe of length 1, in which case I can put something to it even if nobody is reading because I have a buffer, okay? And we do those channels. So let me show you in code how it is done. So I can have a channel C, which is a channel of some type. So channels accept, it's sort of like an array. It has to have a type associated with it. It can be an int, can be a bool, can be a struct, can be anything, can be an interface, but you have to put something into it of some type. So what do we need here? Because we only need to communicate that I'm done, it's sort of like a Boolean value, right? I could communicate what I'm just printing. So I could have a channel which tells other threads I'm currently printing, I'm currently in value X. So then I would integer. Or it could pass the value of the text, of the string. So then I would have a string, right? So I could have this thread generating the strings and another thread actually printing them into a file or into a screen based on the behavior of this thread. And I can have it in 2 different threads. But for the simplicity, let's start with the Boolean case. So I can have a channel that accepts Boolean values, so true or false. And then to put something into the channel, I would use a notation which is like this, and I would say put true into C, right? So if I do that, if I execute this code, so let me do that. I will run it. And well, did I save it? No, I probably didn't save it. So let me run it again. Okay, so oh yeah, so I have an error. You have to say make like this, save it, run it. All right, so look, okay, I will clean it. So go run main. All right, what happened? Well, go compiled my code and start running it, and it said, oh, wait a minute, something is really wrong here because we're getting into a deadlock. Your code is gonna stop and wait forever because you have a deadlock in your code, and the deadlock is as I was explaining, I'm trying to write into a pipe, into a channel, which nobody reads from, and this call is blocking. So this main thread blocks here, but Go runtime knows that there is nobody else, there are no other threads waiting for or reading from this channel, so then it will block forever. It's a deadlock, right? So I can solve it by two ways. One way is I have to have a thread reading from it, from this code, from this channel. The other one is I can make the call, so this call is blocking because I don't have a buffer. The other way is I can make the channel buffered, and I can say it's of length of 1. So you can put stuff to it up to 1 value, and then it will non-block, right? It can hold the channel, if nobody is reading from it, can buffer 1 element. So if I do this, whoops. So let me write this and let me run it. Now it works, right? It's non-blocking again. So if I did see I write 1 more value to it, then we will get a deadlock again, right? Because the channel already has 1 value and I cannot write the second one before the first one was read. So I could make it, okay, let's buffer 2 values, and then it will work. Does it make sense? All right, so I have a concept of a channel, unbuffered, and I can pass this channel to my functions, okay? And then my function takes a third parameter, which is a channel of bool values, and let's call it C. So now I can, when I'm done printing, I can put true into the channel. So now I know I have 2 threads, so I know I have to at least read 2 values from that C to finish executing, right? So reading from a channel is the arrow the opposite way. So if something goes out of C, that means I'm reading from C. If something goes into C, that means I'm putting something into C. So I would have some value here, and then if I want to read, I do this and I can assign it. So I can assign like a Boolean value. So I have Boolean 1 from C and I have Boolean 2 from C. So now, you know, the logic of the code is super trivial. Like I'm not ever writing false. I only write true. So I don't really care what it is, because I know if I read something, that has to be true, right? So if I read 2 values, I mean those 2 threads finished. And then I can print this, right? So because this printing happens really fast, I will say time sleep. Let's sleep for 5 seconds. So I imported the time module, and in those printing, I will do the printing and then sleep for, yeah, maybe we do something else. Maybe we, let's do this, time sleep. So we'll be printing with the delay. Okay, so let's do this now. Yes, it doesn't want to compile because I declared 2 values that I don't use. So I will say I actually don't need them. Will this work? Okay, it will not work because I cannot do this. Okay, so I don't need a return value, so I just read from the channel. So clear that. Let's clear that and go run main. Okay, so we can see the scheduler now takes 1 second to print every line, which means every thread, which we have 2, always have time to execute. So because A sleeps for 1 second after printing the first line, that B gets time. The order sometimes is swapped. So sometimes A gets first, sometimes B gets first. And then we are waiting until all it's done and we're quitting. So we synchronize the threads in such a way that the main thread waits for the execution of the 2 threads, and we kind of synced it through the channel that is a Boolean channel to make it work. If I avoid one of the reads, I only read the first thread finishing, right? So let's try that. I will have those 2 threads running. The first one to finish will tell me that it's done, and then the main thread will quit. And in this particular case, both got done, right? But you could have one of them not quite done and being killed by the main thread finishing, right? Make sense? Do you understand, like, the logic of why I have to wait twice, read twice from the channel? Because I have 2 threads. And this line is executed 1 per thread. So the Go routines are very simple. So creating a new thread and running a function in a separate thread is trivial in Go. You just prefix your line of code with Go. Using channels with in and out functionality is quite straightforward. It's either buffered or non-buffered, and you can write or not, or read from it. You have blocking and non-blocking calls. So this call would block normally until the main thread reads from it, right? So let me try that. Let me try not reading from both of those threads. So what will happen now? If I execute the program, say it again? That's right. So it will terminate, but it will terminate in a different way than previously. So previously what happened? Previously we had, remember we had A being able to run 4 numbers. And we had, the B never kind of got time to do it because A was busy printing numbers, right? Now we will always see the first number printed, either for 1 thread or for 2. Nothing else happens because this line blocks, no, sorry. Yeah, it's about the sleep. Yeah, that's right. Because we're not communicating in the loop. So this 1 line printing is because of the sleep. But the thing is, those threads don't quit. Both threads are still running when the main gets to run because this call is blocking, right? Because this call cannot put true into the channel because nobody else is reading from them.
Shouldn't the main try to inject something so you can actually see it that way? If you try to actually add to C from main and read it from the big numbers instead.
Say it again?
If that one is blocking.
Yeah, this line is blocking.
Yeah.
So if I have a format print line thread tag is done, this line will never reach. This line will never be executed.
If
in here.
If you reorder your instructions, so you actually take one out of C instead of inputting into C there, and
In this line here?
yeah,
Yeah.
and you do it.
So you want me to read from C?
Yeah.
Yeah.
And just comment out the routing,
Yeah.
and you do the opposite in main.
So in main you want me to write to C saying, you know, finish. Yeah.
Probably twice as well, but
Twice. Yeah, I can do that. So
theoretically, we should see that both threads are terminated. If the writing also blocks.
yes, correct. So this line will block until this thread is done and reaches this line. So then it can get cleared by one of the threads, and then moves to this line and waits until this thread is done and goes to this line, and then quits. Yes, that the logic will be maintained, and it will wait for the two threads to finish. That's correct. So we can have it this way. The interesting thing is,
Can you see that?
yes, we can see that. So let's write it. And the interesting thing is that this line will be printed just before this line, right? So it will be printed kind of at the end. So like if I have additional weight, so if I put sleep here for 10 seconds, this line wouldn't be printed for 10 seconds, right? So this line only gets executed when the main thread tells it it's done, right? Yeah, so we can run that, and it carries on as usual. Prints the thing as usual at the very end and quits. So it works. Okay, so there is one more thing in here. The thing is, sometimes you don't want this call to be blocking, or you don't want this call to be blocking. And that's why you need a construct which makes it non-blocking. Okay, so if I in this particular example, it's a little bit tricky, but let's do this. Okay, so the thing is, we need 10 seconds to reach the reading part, right? So if I try to write to a channel here, it will kind of block, right? So if I don't want for it to block, I have to say select, and then you specify. It's sort of like a switch statement which specifies some conditions of working with the channels, and then you kind of do certain things if they are possible, and the line which is possible gets executed. Okay, so if I say write to C true, and then there is some behavior. This case will be executed if I can write to C. If there is, if I cannot write to C, like nobody is reading from C, then this line will be skipped, and the program will continue the execution, right? So if this line cannot be executed, I can have a default case. So I can say default, and I can say format print line. No one is waiting for channel C bulls. So I have yeah. I have this. Let me first try to build it. Yeah, let me just change this back to so let me just check if you can have a select statement. Yeah, select. Yeah, let me just check. Select. Go on. I don't remember the syntax. Maybe you have to have a case. You have to write case, yes. Good spotting. So we have to say, yeah, so it was reading from C, and then we have to say case and write that. Yeah, that looks better. So if I try to build now, it builds, and what it will do is it will execute that block of code with this line not executed because so in case, let's do it. So let's say format print line could write to C. Why? Alright, so that should never happen because I'm making a channel. I don't have any background threads yet. I'm trying to write to this channel, and for sure nobody is reading from that channel at that moment of time. So this line should never get executed. So I get to the default case, and this should get executed. Then I have those two things printed, and then I can what I can do is I can change it to a for loop where I have a boolean. So let's have are we finished, which is no, let's call it are we processing, and it's true. And are we processing? And then we will do this. We will say select. We will delete those two lines, and we will do case for reading from C. So if we can read from C, yeah, and we need to have a counter also, because we have 0 threads currently, so we will say counter plus plus, and the default would be format print line. We just print a dot. No, we're doing your way. So we're writing to C, right? Yeah. Right. Makes sense. You're right. So we have to write to C. Good spotting. So we're writing to C. If we were able to write to C, we make the counter bigger. If counter is 2, right? So after the first one will be 1, after the second one will be 2. We do, then we say format print line, and we will say also are we processing is false. Okay, so from two blocking calls which we originally had, we have now non-blocking call which checks if one of the threads is done. If none of the threads is done, we're just printing a dot in the output. And then if one of the threads is done, we increment the counter. We check at the end of the loop if the counter is 2. If it is, we print both threads are done. Oh, come on. Both threads are done. We mark the loop to be done, and then we quit the loop, we print we are done, and then we done. So we save that, we build it, and we run it. So now we have lots of dots being printed, and the threads are printing. Once in a while you see a blip. That's one of the threads printing the thing, right? And then we say thread A is done, thread B is done, both threads are done, and we are done. You can see that why you have so many dots.
Every time you false or default, you are printing.
Every time I'm doing a default, I'm printing a dot, which is here. But why it's so many of them? Yeah?
The main thread each time it gets scheduled to run, it prints dots.
Yeah. This is the reason. The other threads sleep for a second. While they sleep for 1 second, the main thread is scheduled a lot of times. And that's why it prints a lot of dots, right? If I don't sleep, if I say, oh yeah, print those numbers as fast as you can, right? If we build that, we clear it and we run, what will happen now? I will not see a lot of dots. I see some, but not as many as before, right? So you see when the main thread was scheduled and was just printing a dot, and when the other threads were scheduled and they were printing what they're supposed to print, right? So going back to this, you know Go routine, so scheduling a new thread to run. Super simple with the Go keyword. So running, multiple threads, easy with the just prefixing a function with Go. Using channels for communication back and forth, so to pass something in and to read something from, easy. You just then pass the channel into your function, and then you can communicate with the main thread using a channel. Some problems that you have, some deadlock problems and some issues with this type of concurrency the runtime system can detect and can warn you about. And then the normal behavior is blocking. Even if you have buffered channel, the behavior is blocking if you've already used up the buffer. But if you want the calls to be non-blocking, you have to put them into a select statement. So select statement allows you to have a non-blocking reads and writes from channels. So you can check if something is already available, and if it is, you read from it. If it isn't, you continue with your execution. So now the homework was to write a sleep function. So to rewrite this one, to write your own sleep function, which you implement using a timer, and then you sleep for a given amount of time in your own function without using this function. So how would you implement the sleep? So you have to have a function which starts kind of a new thread, which does something for a second, or is scheduled to run after a second. So we suggest using time after. Time after basically schedules the event in a separate thread, which will send something to a channel after a given time. So if I say time after 1 second, it will kind of notify me after 1 second that something came. So what I can do is I can write a function which says, okay, start this timer, and then the next line of code will read from the channel which this timer puts the value in after a given time. So this call will be blocking. And then when the timer finishes and calls me back with the channel value, I will quit my function. So you can write your own sleep function with 2 lines of code. The first line kind of sets the timer to do something after a given period of time, and the second one waits for this to finish, and then you can re-implement sleep with 2 lines of code using the time after. All right, so let's have a short break because I went over time, and then we continue. So we start at 9:40. Whoops. Good run.
Yeah, you went through quite a lot.
Yeah. Too fast?
No, I don't think it's too fast. It doesn't sense.
Too much to take in.
Might be.
Yeah.
I think it might be because I think this is cool. This is good. This is actually
Yes.
First assignment.
All right. You're welcome. Okay. So we running a little bit short in time, so I will not take any major topics related to server programming today. We will do that maybe Friday or the following week. On Tuesday we're continuing with Linux, so we will dedicate Tuesday to Linux and some of the infrastructure issues. And then we may do a little bit of Go on Friday or next Tuesday. What I want to do is two things. One is JSON. How many of you know JSON? So what is JSON? Yeah, JSON is data. No, plus potentially code. But usually it's used for structured data, right? It comes from Java object notation, JavaScript object notation, so that's where the acronym comes from. In JavaScript, I don't need to use the quotes around the parameters. It's sort of a JSON way of stringifying the representation. And I basically have like a record structure with some key value pairs. And it can be nested. And I can use array to contain multiple struct instances. So there is more discussion on JSON in the previous video that is posted already on the site. You can have a look. The idea here is that you are comfortable writing JSON and reading JSON by hand. So in here we have, we have Bob with a particular properties, name, age, and married. Name probably should be capitalized or not. And the booleans are not quoted, numbers are not quoted, strings need to have quotes, and then I can have nesting. And if I have, if I were to do mapping between a JSON structure into a Go structure, I basically use struct to do the mapping, and I map the properties of my JSON into the fields of my struct. So here I have JSON. So here is a JSON struct, which has it's actually not JSON. It's sort of like JavaScript because I don't quoted the properties. But if I were to have the example, let me. I cannot edit this one, so let me go to to here. So if I were to specify this as a string, I would have an opening and closing bracket. I would have a title, book 1, and I would have comma. I would have another type, which is desk, my description of the article, and then I would have content, which is the content of the article. All right, so this is itself a string, which is a JSON representation of some article. And then I would like to map it into my internal representation inside Go. So I would declare a type, which is a struct, which represents my struct, my structural data. And I say what sort of properties I will have, and how do they map into those title, desk, and content, right? So for my article type, I declared title, desk, and content with capital letters. I can declare whatever I want. I can change desk to be description, but it maps to a JSON which is depicted by desk, right? So those values here, what I need to have in my JSON, and those values here, those names, are whatever I want, whatever makes sense. It kind of makes sense to make the mapping readable. Like if I completely change those names, then it will be difficult to keep a mental model of what is my Go structure and what is my JSON structure, right? So typically we map them sort of one-to-one. And I was explaining in the first lecture, because we will be using a parser to parse and pretty printer to print JSON and to parse JSON back and forth from the internal article struct, we have to have those capitalized. So no matter what you're doing inside your JSON, no matter whether you have small or cap letters here, you have to have caps here. Otherwise, those fields cannot be accessed by the parser package and they cannot be properly handled. It has to be publicly visible. So your type and your fields have to be publicly visible, and then you map them into the tags that you have on the JSON side. So that's all there is to it. We have some examples of how to do the parsing later, but all I wanted to explain is just the structure of JSON structs and the mapping between JSON structs and the Golang structs. It's quite trivial. You just have to remember to use a kind of a backticks with JSON, colon, and then in quotes the actual properties or tags that you use inside your JSON. The previous year I spent a little bit more time describing what JSON is, so you can have a look. So in the remaining 6 minutes, there is one more thing that I wanted to talk, which last year video doesn't talk about, and that's errors. So in Go, there is kind of like a pattern, because Go doesn't have exceptions. In C++ or in Java, if something unusual happens, you raise an exception, and then you have a try-catch block, and then you handle the unusual behaviors by the exception handlers. In Go, you don't do that. You have errors. So if you have a function, so let's say I have a function, function f, which takes int and does something. And then if this function can potentially result in an error or exception, I have to handle it. So I have to have a mechanism for doing this. And the way Go idiomatically handles exceptions, which are called errors, is by having a return. So let's say my function f takes an integer and returns an integer. And it, let's say if I is 42, it's an exception. It's like, I cannot deal with 42, okay? Because it's the answer to the universe, so I have to throw something, right? Yeah. Yes. But for everything else, I just return I, okay? So now I have this exceptional situation, like, okay, it has to blow up, but we have no exceptions. So how do I deal with it, right? So let me clear this. So I have, I call f with 3, it will work fine. I call f with 42, and it will blow up. And then I call f with 1, and it should work fine, right? So the middle line here is the problematic one. Normally, I would have try catch block around those functions to see if everything is fine. But in Go, we don't do that. We say, well, the function can, okay, let's say I have a return value 1 for the first call, and I have return value 2 for the second call, and I'm doing something with them, right? So to handle errors, we have to pass an error back to the caller, and we use an error type. So if we have an error, we pass the error. If we have no error, we pass nil. So if I am in normal behavior, I say, okay, the second parameter, the second return value that I'm returning is nil. So I don't have any error. But in this case, I have to return something, so I will return I, and I have to return new error. So we have a kind of a utility method called reverse. Yeah. So is it? Yeah, let's try that. First, let's try if it builds. We have a missing. What is the problem? Missing function. Yeah, maybe we need brackets here. Good. All right, so yes, some C flavors. Okay, let's build it again. Yeah, undefined errors, so the import didn't work that well. Let's try that. Another one.
So it expects comma, semicolon instead of comma.
Yeah, you're not supposed to use commas are an import anymore.
Good spotting. Okay, well, we have it. We build now. Okay, so let me just check it. Go new error. There is just new error, new. It's called just new. Yes, not new error. Okay. So we don't need this. Great. So what it complains now is that because we're returning two things, I have to catch two things here, right? So I have an error E that I will reuse. Go normally, if I was returning two things and I said assign me the first thing this function returns to error1 and assign me the one to error, I cannot do the declaration again for the same variable because I've already declared it. But because I don't want to have multiple error variables like kind of a variable creep, if it is an error, Go allows me to do this in a single line because that would be a nuisance to redeclare this one, right? So now I have to say if E is nil, then I do my normal behavior, else I have to handle the exception, right? So if I say, okay, if I have an exception, I have to handle it. And the same here. If I have an exception, we have to handle it. So we say format print line got an error, and we print E. Alright, so now if we build this, yes, we're not using the R1 and R, so we just print them. R1 and R2. And we run the beast. So we run it. And it says, yeah, I got an error, cannot deal with the answer to the universe. And then it prints 3 and 42, right? Because even when we got the error, we still return the value. So, in very nutshell, that's how you deal with functions which can return errors. And you will notice that for I/O, all the I/O functions for reading and writing, they return you something or they return you an error. And then you have to check for the return values. If you don't care, you can ignore it. So if you don't care about something, like I don't care about R2 and R1, I only care about if I got an error, and I'm not printing them at the end, you can use the underscore to ignore the part of the return value. If you don't want to care about the error, you can say underscore for the error, right? But it's not a good practice to do that. So if I build it again, if I don't have any new variables, I cannot do this. So I have to say for the second one, I have to say this. If I wasn't declaring R2, I can do the declaration, but now I cannot. And I cannot here neither. Number 7. Yeah, you get the gist. It's just a string. Yeah, so the error is effectively just a string. You will notice that an error is an interface which has a method called error with capital E, which returns a string, right? So errors are just anything. Your struct can be an error. You can have multiple things inside the error which just return a string.
Okay, so you're actually not, so it's only a string, nothing else.
I mean, you can have additional things there, but an error is kind of maps to the interface which has this error method which returns a string. So it's kind of rather trivial. If you go to error, you will see that the built-in type error. Error is just the interface which has a single method called error which returns a string, right? So your errors kind of map to some description effectively. So that's a very simple error handler. Yeah. Yes? Yes, so if you have your own struct, let's say you want to catch some errors related to division by 0 or whatever, right? If you were to store the value which was throwing the error, I would have a struct which would have some fields, and this struct would have a method called error, and then I can, pass this struct back, right? So I can then cast it to my type and get extra information from the error that I passed, right? Because what I'm doing here, I have to return a second thing. It can be your struct, right? So the error can be much more complex thing. The only requirement is it has a method called error with capital E, right? Like in the declarations. Yeah?
Does Go have some way of some type of reflection to find out which types of return values?
No. So you will have to kind of know. You can check if the particular thing that you're getting is of certain type. So it has like a type checking. So you can say, oh yeah, are you instance of this struct? And then I can cast it to it, right? So if you cannot cast to something, it will return false. And then you can check for this. And if it can cast, it will return true, and you can use it with this cast, right? So there is a construct for casting. But you cannot say, tell me what type are you, right? You have to sort of hard, yeah, exactly, yeah. Yes?
I learned that you shouldn't just don't just run out full market information. You just call the function.
Yeah. Yeah, that's right. But in that case, you would have to have something else than an error, right? If you want more complex API, you would have your own kind of error type, which you will return instead of just returning an error, because this one is like just this, right? Yeah. So to have a more robust polymorphic behavior, you would declare your own interface. You would say my function returns this new kind of error handler, and then I return instance of that, right? You can do that. I mean, you don't have to use error, but it's a lot of standard APIs, they use error. Yeah. Any other questions? Great. So we finish here. And on Tuesday, we will continue with the infrastructure and with Linux. Thank you very much.